Okay, well, good morning. So Friday morning, last day of full sessions. How many folks here are coming to LambdaConf for the first time? Oh, wow, that's great. And how many of you would consider yourself beginners in Haskell? Oh, awesome. And for the rest of you, how many are interested in hearing a talk pitched to beginners in Haskell? Okay, so I think we have everyone covered because that's what this is. All right. Booleans considered harmful. So note that the title says, for beginners in Haskell. I really do mean that. I'm going to be focusing on trying to build the basic intuitions, not on technical precision. I am going to assume you know some basic Haskell. Also, there are a bunch of slides here, so I would prefer that we hold questions for the end. That will take more than about 10 seconds. If you have a quick clarification kind of question, that's totally cool. But anything that's going to lead to a discussion, I prefer to do that toward the end. So who am I? My name is Stephen Pimentel. I work as a machine learning engineer at a tech company in the San Francisco Bay Area, mostly working with Python, even though I'd love to be using Haskell. Before that, I worked at a distributed database startup called FoundationDB. The term Boolean blindness was introduced by Dan Licata, then at CMU, now at Wesleyan University. Here's an early reference in his lecture notes. The term has since become part of the folklore of functional programming. You often hear people sort of casually toss it off in the middle of a talk without explaining what it is or what they're talking about or why you should care. Boolean blindness refers to a weakness of Booleans that causes a number of problems. To address these problems, we'll look at ways to eliminate both Booleans and the conditionals in which they're used. Bool is an information-poor type. A Boolean value conveys one bit of information. In fact, bool is one of the least informative types. Only unit is less informative, as it has only a single nullary constructor and yields 0 bits of information. Computing a Boolean value reduces a potentially large amount of information to a single bit. This bit often fails to convey information that you need. To recover that lost information, you have to examine or even re-execute the computation that produced it. Boolean values are used to branch in conditionals. A common anti-pattern occurs when, within a branch, you end up performing a test to recover information that you actually had when computing the Boolean value in the first place. Say you're a programmer new to Haskell, and you decide to write append, list append, for yourself as an exercise. You might write a naive version like this. The code computes a Boolean value from the first input list, requiring the ek constraint, then branches on it. Note that you aren't going to compute a Boolean value once. You're going to compute it n times, one for each call to the recursive function. Also, in the else branch, we have to call both head and tail on the first input list because we know nothing about it other than that it's non-null. In more complex code with nested conditionals, these problems only compound. But if we get rid of the Boolean value in favor of pattern matching, we solve all of these problems at once. In this version, we compute no Boolean value, require no ek constraint, and require no calls to head or tail, because the relevant data has been exposed by the pattern match. So here we have our first principle. Types that fail to capture needed information make you do redundant work later. Information poverty leads to a number of problems with partial functions, erroneous arguments, and locality of control. And we're going to kind of look at all of those. A partial function is one that is not defined for all values of its domain or input type. A total function is one that is defined for all such values. In practice, a partial function will throw an exception when called with a value for which it is not defined. Booleans are often used to avoid calling partial functions on values for which they are undefined. Say a new Haskeller decides to write a lookup function for association lists. The first attempt might look like this. It's a very natural recursive function. It's also partial and will error out if the key being looked for, variable x, isn't present. You don't want an error, so when using the lookup function, you need to first check that the value being looked up is actually present. Say we're storing the numeric equivalents to letter grades for some school application in the association list, and we want to add extra credit to one of the grades. We might have code like this. Contains is our function for checking the presence of a key. The primary function either returns the numeric grade with an additional grade point of credit, or 0 as a default if the key was absent. One problem with this code is that there's nothing to prevent us from incorrectly trying to access the grade in the else branch. So, for example, this incorrect function will still compile. The else branch tries to access a key that isn't present, but the compiler doesn't know that. There's nothing that the type checker can see that would indicate that this isn't correct. This leads to our next principle. Information-poor types make you touch. Touching, in this context, means checking for domain values for which a partial function would be undefined. Using Booleans in this way is a poor solution to partial functions for a couple of reasons. First, after you have touched, when using the resulting Boolean to branch, the type system cannot help you control what code is executed in which code path. Second, nothing in the type system makes you check that value in the first place. This is related to the problem of null references, which Tony Hoare called his billion-dollar mistake. A better approach is to use the type system to explicitly account for null values. In other words, to rewrite partial functions as total ones using richer types. In Haskell, you often do this by wrapping a simpler type in a higher kinded data type like maybe or either, especially as return types for functions. Here's the definition of lookup in Prelude, using maybe as a return type. Unlike the previous definition, this function is total. We get a perfectly sensible nothing value when the key we're looking for is absent. Now we can write the add extra credit function without a Boolean check that the key we're going to look up is actually present. This version has a valid value when the grade is not known. Even better, we won't be tempted to make the mistake of trying to access the numeric grade x in the nothing branch because it isn't even in scope there. Here's a version of the function where I've tried to mistakenly access the grade in the nothing branch. But unlike the erroneous partial version, x is not in scope in the nothing branch, so this version won't even compile, which is a good thing. This is the type checker preventing us from making a mistake. We can now complete the previous principle. Information-poor types make you touch. Richer types let you see. Seeing means that when you match on a type like maybe A, you naturally know whether you have an A to work on. It therefore helps you write total functions. The distinction between the types A and maybe A is communicated and enforced by the type system. When using maybe A in a return type, the type system ensures that the caller handles error values by eventually casing on the maybe, even if only at the end of your computation. So higher-kinded types let you rewrite partial functions as total ones. By shifting to a result type of a higher cardinality, you can handle what would otherwise be undefined values of a partial function. Next problem. A Boolean value tells you nothing about its intended use. To know how to use it, you have to know its provenance, where it came from. This makes it easy to pass the wrong values to an API. You can try to ameliorate this problem by giving Boolean variables meaningful names, but the type checker doesn't care about variable names, and so can't give you any help here. The problem becomes worse when a function has 2 or more Boolean arguments. Say we're writing a function to validate input strings. We decide we'll need to do 2 kinds of things. Normalize the input by transforming it in some way, and apply predicates to check its validity. Our first naive version has 1 transform and 1 predicate, and uses Boolean parameters to control whether to apply them. The first conditional normalizes the input by removing spaces, if indicated by the flag. What are the weaknesses here? Well, all bools look the same to the type checker. So with this type signature, the type checker can't help you remember what the parameters mean or prevent you from calling them out of order. In short, Boolean arguments are error-prone in that they're easily called out of order. One way to safeguard the use of parameters is by making them custom algebraic data types rather than Booleans. Now the type checker will guarantee that only appropriate values can be used for a given argument. So we might do something like this. By giving each parameter a type with named values, the type checker can ensure that the first and second parameters are called properly. Having said that, toStrip and printable are still isomorphic to Booleans in that they have 1 bit of information each, and they are still used in conditionals. There's actually a deeper problem with Booleans having to do with locality of control. Recall Edsger Dijkstra's polemic against gotos. Like a goto, use of Booleans often violates locality. Why? Booleans can be produced by any Boolean valued function, but they can only be used in one way, to control branching in conditionals. When a function evaluates to a Boolean value, it gives you a bit. That bit can be passed to some distant location in the code where it is used in the only way it can be, to branch in a conditional. When the bit is finally used, it's often no longer easy to examine or reason about the computation that produced it. Consider this from a debugging perspective. You can write a function of arbitrary complexity that produces a Boolean value, then passes it to some distant code. The stack of the computation producing the value has been thrown away by the time you use the value, which shows up only as true or false. In other words, Boolean values leave behind the context that produced them. You can always eliminate Booleans by moving the computation that produces them to the place in the code that needs to branch. The value of this approach is that the reason for a decision and its consequences will appear in the same place. So locality is preserved. From a debugging perspective, if you look at the stack trace of such a program, you can see the reason for any branches that are taken. A literal-minded way to follow this approach would be to inline the decision code. But Haskell makes it easy to do better than that. You can have the caller pass the computation to the function that needs it as another function. In Haskell, passing functions is idiomatic. So this is quite natural and results in code that is easier to understand. Passing functions allows the function caller to directly pass its computational intent to the callee. Returning to our input validation example, you can replace conditionals based on a Boolean parameter with functions that perform the effect of the conditional. First, we can replace the space removal flag with the transform it controlled. This change will let us support an arbitrary transform rather than just white space stripping. In fact, it will support any number of transforms because their input and return types are both string. So they can just be composed and passed as a single argument. And if you don't need a transform, you just pass the identity function. We can replace the conditional controlled by the printable flag in the same way, by extracting it into another function. This also makes the code more flexible by supporting arbitrary predicates. The validate function has now been simplified to the point of triviality. It does nothing but apply the transform before it applies the predicate. But that's an artifact of starting with an already pretty simple function. While your code generally will become simpler using these techniques, it won't go that far. A bigger problem is that while we've gotten rid of its Boolean parameters, validate still returns a Boolean. So its caller will still be working with a Boolean. We've already seen that we can use higher-kinded types to eliminate Booleans. Here, we've changed validate to return a maybe string. This works, but we've kind of taken a step backwards in terms of complexity. Moreover, this pattern doesn't scale well. As we add predicates, we're going to get a cascade of conditionals to apply them. How can we improve this function? If we change its signature to supply a list of predicates, can we just handle them all at once? Yes. It turns out there are a few ways to do this. One way uses all. All takes a single predicate and applies it to a list of values and returns the conjunction of the results. However, there is a catch here. There's a problem. What we need for validate is the inverse. We want to apply not a predicate to a list of values, but a list of predicates to a single value. We can achieve this inversion with a clever use of $sign. The right section of $sign takes a function and applies it to an already specified value, which is exactly what we need. Ursula K. Le Guin wrote a novel called The Left Hand of Darkness that I'm sure many of you have read. If I ever write a science fiction novel, I'm going to call it The Right Section of $sign, and its theme will be the manipulation of arguments. Here's our scalable version of validate using all with the right section of $sign. This is good, but we still have a conditional in there. Can we get rid of it? Well, we can at least factor it out using a helper function. This is probably the most obvious helper function to use in that it corresponds exactly to the conditional we just saw in validate. It takes a Boolean flag and uses that to select between maybe values. That may not turn out to be the best approach, but let's give it a try and see how that works out. By substituting in the maybe bool helper function, we get this definition. It may be a little better than what we had before, but I don't love it. One thing that's not so great is the way the output variable is being threaded through the definition, appearing twice in the final line. Here's another way to write that helper function. Instead of taking a Boolean flag, we'll adjust a predicate to return a maybe string instead of a bool. One thing to notice about this helper function is that if we apply it to a predicate, so partially apply it to a predicate, we get a function of type string to maybe string, which has exactly the right shape to use with a monadic bind. So let's do a little review here. If you haven't seen monads or would like a reminder, monad is a higher kinded type that supports sequencing of computations. The bind operator here takes some structure over a type, that's the MA, a computation from A to a structure over B, that's that second argument, A to MB, and returns a structure over B. Because the result type is another monad, the MB, these binding operations can be sequenced. Types with monad instances that are commonly encountered in Haskell include state, error, continuation, and I/O. And, usefully for us, maybe has a monad instance as well. It'll turn out that the reverse bind will be the most convenient for us to use. It's exactly the same as bind, except it takes its two arguments in the other order, the reverse order. And we'll be taking advantage of maybe's monad instance. So the signature of reverse bind with maybe will end up looking like this. You take a computation producing a maybe A, and you get your output maybe B. So here's our new solution. We map our new helper function over the predicates to adjust their signatures. We take the transformed input wrapped in a maybe constructor and use that as the initial accumulator of a right fold. Our fold operator is the reverse bind. That's kind of compact, so I'll give you a moment to look at that. It's easiest if you think about it from right to left. At least I find it so. So we're using our helper function, that's the maybe pred, to sort of adjust the signature of the predicates, that list of predicates. We're mapping maybe pred over that list. We're taking our input, applying the transform, then wrapping it in the just, so we have just the transform input. That's the initial accumulator to the fold. And then what we fold over the whole thing is that reverse bind. So here's a look at how actually applying that to an example would reduce. We're folding over a list of adjusted predicates, so the fold takes each one and applies it to the maybe string. Now, a nice thing about this, if nothing is encountered at any point, we simply short circuit. So if the first predicate were to yield a nothing, then we're not going to even look at the rest of the list because we know in effect that's and false, a conjunction with a false in it. So we get some computational efficiency there. And assuming all of the predicates pass, we get just the transformed input. In this case, just foo. Sure. It's worth pausing to appreciate this for a moment. In the final form of the function, we can handle any number of transforms and predicates. There are no conditionals and no Booleans being explicitly referenced. Plus, the function definition fits on one line. So it got more general, less error prone, and more compact all at once. The signature of a function amounts to a little API in which arguments are used to convey computational intent from the function caller to the callee. Boolean arguments reduce that intent to a single bit, which can be used only to branch in a conditional and select a code path. As a result, Booleans give you an information-poor API that is error-prone, for both the caller and the callee. You can improve your API by using richer types and getting rid of them. All right. Any questions? Oh, go ahead.
The pattern of swapping, turning things in from partial to
Right.
total or maybe.
Uh-huh.
Is there an anti-pattern around returning a pseudo-identity value as your maybe instead of nothing, so that the domain of the return value is always within the same domain, and you don't have to case or pattern match on nothing at all?
Well, it would have to be distinguished in some way to know that you hit that case, right? So it would really just be a renamed nothing. I mean, even if you like had some use case, say, where you knew your return value had to be a number greater than 0, and you chose to use 0 as a kind of, as your, in effect, the nothing. You're still going to case to determine whether you hit that case or not, because the whole point is that's a different situation, and you need to distinguish it from the situation where you had a real return value. Like you wouldn't want to, if that 0 is simply being used as a flag meaning no value found, or wrong, wrong input or something, then you wouldn't want to take that 0 and use it and further use it as though it were just like 3 or 4, just like it were a valid value. You have to distinguish that, because it's not a value value.
So would you consider that an anti-pattern?
Yeah, well, it's sort of an ad hoc, you've sort of rolled your own maybe, and why do that? That's just going to confuse people. I mean, maybe is the idiomatic way of doing that exact thing in Haskell. So yeah, that would be an anti-pattern.
Kind of going to the idea of rolling your own maybe, do you think there's some kind of value in actually doing that? Because I've seen that maybe it encapsulates one simple idea, but sometimes the nothing represents there is no computation that happened. Sometimes the nothing can mean, hey, I don't want you to do anything additional here, so just use a nothing to represent that don't run that computation that might happen. Do you think sometimes that using kind of like freedom versions of maybe would be better because it helps you know what the actual thing means?
Absolutely. So it's not just maybe. Maybe is not like the only choice here. So I said higher kinded type, so there's either. Either lets you, so the idiom with either is right will typically enclose the actual valid value, and then left will enclose an error message or maybe some code for what went wrong. So rather than just having that single nothing, meaning, not a good answer, but I can't give you any more information, you could actually, there might be 4 or 5 possibilities, and you could encode those in the left value for an either.
So in such a situation, though, would you just do a new type over the maybe, or would you actually create your own like data type that's just the same thing as one?
If it's really isomorphic to maybe and you're not doing anything really different, I would prefer just using maybe, because it's immediately recognizable. Any Haskeller will see that and know exactly what it is. And a lot of the standard libraries use maybe. So if you use functions from the libraries, you're going to be using maybe anyway in a lot of those cases. Now, if in fact you're doing something a bit richer, then by all means, use a new type that captures the thing you want to do. Yep.
So the right value could be the string, average. The left value could actually be the predicate.
The predicate on which it failed, right? Right. Yep.
So in your example, before you came to the final solution of the problem line, you had something that was functionally the same. You said you didn't like it because it had output written twice on the same.
That one, yeah. It's okay. It's just,
The same thing, right?
yeah, that is yes.
I found this more
Nope. No, there's nothing profoundly bad about this. And I understand why a fold over a reverse bind is not the immediately most readable thing if you haven't like played with that before. Having said that, if you've used fold a bit and bind a bit, it is a very sort of nice, clean, compact thing. So I personally prefer it, but this is not horrible. Anything else? Oh.
Do you ever find yourself switching to types that give less information, so consumers don't have to worry about the full domain space? So like using Boolean or something that has less possible inhabitants, just so implementing the function can work constrained?
Not really, because like a maybe only adds to the cardinality of a type by 1. Right? I mean, it's not as if you're opening up the possible return types in some hard-to-handle way. I mean, there might be some example that you could construct where that would make sense, but not.
Well, if you're validating, like, let's say you're validating a string, and the return type, you're not transforming the string at all.
Okay.
The return type could not be the same as the input. So you now have the possibility that someone actually changed the value. But if you return a Boolean, the only significant values are false return.
Sure. You can imagine a use case in which you'd want to do that. Sure.
What's the performance difference?
Ah, very interesting. Yeah, I have not profiled them. I ought to. I don't expect it would be hugely different, but it'd be interesting to see on a big input which one was actually faster.
Is there a way that you could symbolically argue for what the performance is going to be, or is it profiling after the fact the only possible way to determine?
Profiling gives you ground truth. You can try to reason about it, but even knowledgeable Haskellers would often be wrong, simply because GHC does. You would have to know the optimizations that GHC would apply to it, which can be tricky.
Have you encountered a situation where Boolean really was the right answer for something?
I mean, so I do Python in my day-to-day, so I see Booleans all the time, but for all the reasons described here, I think it really is true that it would rarely make your code better to do Booleans and conditionals versus some of these techniques. Anything else? I can give them to you. I don't have them posted right now. Feel free to snag me. All right, well, thank you very much.